Hi everybody, welcome back. We're going to go over the last two sections of chapter 19. And in these two sections, we're going to be looking at the magnetic field created by a wire. So we know that forces are exerted on wires in magnetic fields, right? And we use the right-hand rule to determine the direction of that force, but wires carrying current, moving charges, also produce magnetic fields. So we're going to develop another right-hand rule to help us find the direction of the magnetic field created by a current carrying wire. And then we're going to talk about Ampere's law. But first, the way that we find the magnetic field created by a current carrying wire is we stick our thumb in the direction of the current, and then our fingers are going to curl around in a circle around that thumb current. And where our fingers pause in relation to the thumb is going to give us the direction of the magnetic field. So for example, in this position, the fingers are on top of the current thumb, right? And so those fingers are pointing to our left, if you're looking at the screen. So if we were to keep curling those fingers down, right, we would be to the left of the thumb and the B field would point down. And if you keep rotating your hand so that your fingers are below the thumb, you're gonna see that the B field points that way. And then finally, if you kind of turn your hand upside down, your fingers, when they're to the right of the thumb, they're going to be pointing up. And so this is a little bit hard to see in this point of view. So what I'm going to do is I'm going to draw these wires. Well, I'm going to draw two wires, one going into the page and one going out of the page, right? So that we're looking at it from this point of view, okay? So let's draw a wire that is coming out of the page. There's the current coming out of the page at us. So our thumb is going to point out of the page, and we're going to curl our fingers around. And when my fingers, I'll draw this little circle here, just as our guide, okay? When I'm directly on top of the current, the B field is going to point this way, okay? When I am to the left of the current, the B field will point down. When I'm below the current, the B field will point to the right, and when I'm to the right of the current, the B field will point up. So the B field makes a counterclockwise circle around a current that's coming out of the page. So you see, this is the same drawing, but two different perspectives. And this perspective is sometimes a little bit easier to digest. Let me give you another perspective. What about a current carrying wire that's moving up? Well, we point our thumb up, and when your fingers are to the right of your thumb, you're going to see that they are pointing down into the page. So the B field to the right of a current carrying wire is pointing down from this perspective and pointing up from this perspective. What about below the wire? Below the wire, it's pointing to the right. I'm sorry, to the left. And then if we're above the wire, it's pointing to the right. Okay? So 3 different perspectives to look at here. Let's draw this perspective over here, but with the current going into the page. So we're going to point our thumb into the page, and we're going to curl our fingers around, and you're going to see that they're going to go in a clockwise motion, right? So at the top of the clock, the B field is pointing to the right. At 3 o'clock, the B field is pointing down. At 6 o'clock, the B field is pointing to the left, and at 9 o'clock, the B field is pointing up. Do you see that? So in this perspective where the current is moving down, we're going to point our thumb pointing down, and then our fingers on the left side will be into the page for the B field. Below the wire, they're going to be going this way. To the right of the wire, they'll be pointing out of the page. And then above the wire, they'll be going this way. Okay, so those are the kind of, different orientations and the two different ways that the current can point, right? We're looking at different perspectives, but in each perspective, we're examining the two different orientations of the current, whether it's going, in the page or out of the page or up or down. Okay, so that's how we find the direction. So what about the magnitude? What's the magnitude of this magnetic field? Well, the farther away you get from the magnetic field, from the current, the magnetic field is going to decrease in the same way that the electric field decreased the farther away we got from a charge. And so the equation for the magnitude of the magnetic field is going to be mu naught times the current divided by 2 pi r, where r is the distance from the wire to where the field is being measured. So in this case, when I is like this, and we're trying to find the B field, okay, this is R. R is like the radius of a circle, right? Because around a straight wire, the magnetic field is a constant value at any R, at any value of R on this circle, right? That's what this is saying, because I is a constant for that one current. Mu naught, what's mu naught? Mu naught is a constant, a lot like epsilon naught. Mu naught is 4 pi times 10 to the minus 7. Okay, so that's the value of mu naught. And then we have divided by 2 pi r. Okay, so that is the magnitude of a magnetic field due to a straight wire. A long straight wire, okay? And you can see that this magnitude is constant at anywhere on a circle, okay, around the wire. What about other geometries of wires? What about a curved wire? So what we call a curved wire, it could be referred to as a coil or a solenoid. You might even recognize it as a helix, right? So this is a common shape to make a current carrying wire. And that's because when you curl that wire around like this, what happens is if you take your thumb and you follow along the current direction and you kind of like use your thumb to trace that curvature, what you're going to find is that your hand or your fingers are always going to be sweeping when you're inside of the wire. It's going to be sweeping in this motion, okay? So what that means is that when you curve a wire, you actually get a straight magnetic field, right? Here, when you have a straight wire, you get a curved magnetic field. But when you curve the wire, you get a straight magnetic field only in the center of that coil. And so this is a very common shape that we use to make magnetic fields. So for example, in an MRI machine, why do you think the MRI machine looks kind of like a circle? Well, you know that there's a strong magnetic field inside of that MRI machine, right? But that circular shape is actually all these coils of wire, okay, going like this and creating a really strong magnetic field either into or out of the plane or out of the center, okay, depending on what direction the current is moving, right? If it's moving this way, then the B field will be going into the page. And if the current is rotating that way, then the magnetic field will be out of the page. So, right, this is a very common geometry. And so it's called a solenoid. So when you wrap the wire around in a circle, okay, and your current is moving around in a circle, you get a straight magnetic field in the middle. Okay, and that's called a solenoid. And so we're going to be talking a lot about solenoids in chapter 20. We're not going to be talking about it in chapter 19 a whole lot. So just table this information until we get to chapter 20, okay? So here's the magnetic field for a solenoid, okay? Inside of a long, straight solenoid, okay? I know there's like the words long and straight are here, but what they mean is a really long solenoid that isn't like crooked, okay? So the magnetic field inside of a long, straight solenoid, we know points like this. And this is its formula, okay? So notice that there's no 2 pi r here, right? It's simply mu naught times n times the current. So what's N? N is the number of windings per meter. So basically, if this is a meter, okay, it's the number of windings, the number of turns. So 1, 2, 3, 4, 4 turns per meter. If that's 1 meter, then the N here is 4 turns per meter. Meter -1. Okay, you can rewrite this as little n as big N times divided by the length, right? So another way to write the magnetic field would just be mu naught times the total number of turns current times the full length, or divided by the full length of the solenoid. But this big N over L is simply little n. Okay. So, so again, table this information for chapter 20. Okay, there's nothing in your homework that has to do with the solenoid for chapter 19. And so the question is, okay, how did we know this? Like, where did these formulas come from? Okay, well, the formulas came from an application of Ampere's law, which is a lot like Gauss's law. It's a similar type of law. So just to review, remember Gauss's law was the electric field times the area equals the charge enclosed over epsilon naught, right? So we were looking at like a surface area, and we were looking at the electric field going through the surface of the area, okay, right? We had to do the flux. And that multiplication was equal to how much charge is inside of that area. Well, now let's look at Ampere's law. Ampere's law, well, it's got this crazy looking formula, okay, on the left-hand side. But I'm going to explain it to you. It looks a little crazy. It's the product of a loop times the magnetic field value at every point on that loop. So remember how we had a current carrying wire, right? And the magnetic field made a circle or a loop around that wire. Well, that magnetic field value was constant everywhere, right? Because its value was given by mu naught I over 2 pi r. So since this circle everywhere has the same radius r, the magnetic field is going to be the same everywhere on that circle. And so if we take that value of B and we multiply it by the total length of that circle, which is a circumference, right? Then that multiplication of the circumference of the circle times the magnitude of that magnetic field, well, guess what that's going to be equal to? That is going to be equal to mu naught times the current running through that loop or that circle, okay? So you can see the similarities here, right? Instead of in Gauss's law looking at electric field penetrating an area, we are looking at the current or the magnetic field created by that current along a loop, okay? And so that loop can be a circle, that loop can be a square, okay? So if I have a bunch of currents in a line coming out of the page and I draw my loop like this, okay, the delta L here is going to be the perimeter of my loop. But it's not going to be just the perimeter times the magnetic field. It's going to be the perimeter of, it's going to be the length of this side of the loop times the magnetic field here. It's going to be the length of this loop times the magnetic field at that point. It's going to be the length of this loop times the magnetic field at that point, and so on, right? We got to add them all up. Because when you have a square loop, the magnetic field is not going to be the same at every edge of the loop, of the square, just like it was for the circle, right? When you have this loop, the magnetic field is going to be different. So you have to find the magnetic field for each side of the square. We're not going to be doing anything like that. I'm just kind of explaining it to you, like how it works. So when you do the loop like this, I'm just explaining the steps for you because this is how the solenoid equation was derived. Okay, but I'm not going to ask you to derive it. I'm just kind of explaining it to you how it was derived, okay? So that's how we do the solenoid equation. But this is basically Ampere's law is where how we determined the magnetic field value due to a long straight wire or due to a solenoid. Okay? So for the last section of this chapter, we're going to combine the two ideas, right? The ideas that a force is felt by a current carrying wire in a magnetic field, and that a current carrying wire produces a magnetic field. All right, so we're going to combine both of those concepts. And what we're going to look at to combine those two concepts is two wires next to each other. Okay, so in this picture, we have two wires next to each other. We have a bunch of vectors there. I'm going to erase them real quick because we're gonna develop the directions. I'm not going to erase the current though. Okay, we're going to find the B field direction and we're going to find F. All right, as a practice. We're going to apply two different right-hand rules to do that. All right, so let's say we're starting off here with two wires, okay, and their currents are moving in the same direction. Okay, their currents are moving in the same direction. So let's say we want to find the force on the second wire. What is the second wire feeling? Okay. Well, the first wire is making a magnetic field, right? And that's the magnetic field that the second wire is going to experience, right? The second wire is not going to feel its own field. The second wire is only going to feel the field due to the first one. So let's find the direction of that magnetic field. So we're going to stick our thumb in the direction of wire 1, okay? And we're going to curl our fingers around and we're going to stop when we are to the left of wire 1. So let me draw side by side, right? I'm going to draw this picture from this perspective, or if I'm looking at it like this with my beautiful eyelashes. Okay, I'm looking at it like this. And so here it is on this side. This is, right, they're both pointing out of the page if we're looking at it like this. So if this is wire 1 on the right and wire 2 on the left, wire 1 creates a magnetic field and it's, constant in a circle around I1. So if I'm drawing a constant radius around I1, I'm going to point my thumb into the page of right where I1 is going. I'm going to curl my fingers around, and when I get to this position, the magnetic field is going to be pointing up. Do we agree with that? All right, thumb into the page, swirl it around until my fingers stop to the left of my thumb, and the magnetic field will be pointing up. So this is the magnetic field created by current 1 at the location of wire 2. So that is this vector right here. All right, so we figured out, okay, great. Wire 2 is sitting in the field created by wire 1. What force does it feel? Well, let's do a second right-hand rule, right? Fingers in the direction of I2 of my right hand. That means my thumb is going like this, okay? And then I am going to curl it into B1. So I'm going to have to flip my hands upside down. So this is still my right hand. I'm looking at the palm up. I'm going to curl it into B1. Curl my fingers into B1. And you're going to see that my thumb is pointing towards I1. Okay, my thumb is pointing towards I1. My thumb is the direction of the force. So this is the force that wire 1 exerts on wire 2. Okay, so we used two right-hand rules. The first one was to find the direction of the magnetic field. Second one was to find the direction of the force. And so we can do the same thing for wire 1 now, okay? Wire 1 is feeling a magnetic field. He's not feeling his own, he's feeling the field created by wire 2. So I'm going to put my thumb in the direction of wire 2. Okay, put my thumb pointing into the page, and then I'm going to curl my fingers around until I get to the right of wire 2. So if I draw I'm going to erase this circle here. Right now I'm going to draw my circle around wire 2. Somewhat, just pretend the radius is constant there. Right, thumb is into the page, so what I'm going to see is that the magnetic field is actually pointing this way. The magnetic field created by wire 2 is pointing down. Okay, so the magnetic field created by wire 2 is pointing down. And so now I'm going to use my second right-hand rule, well, technically the first one that we learned. We put our fingers in the direction of the current, and I'm going to be looking at the back of my right hand, and then I'm going to curl them down into B, and you're going to see that your thumb is pointing towards the other wire. Oops. Here we go. Thumb pointing towards the other wire. That's the force that the second wire exerts on the first one. Okay, towards the other one. And so what you can see here is that there is an attractive force, right? The force vectors are pointing towards each other. There is an attractive force between two wires when the currents are pointing in the same direction, okay? So when currents are pointing in the same direction, attractive force. We can go through this whole business again for opposite wires. And when we do that, I'll let you do it for practice, but I'll write the vectors here. What you're going to see is that the B fields actually end up pointing in the same direction. And that ends up making the force pointing away. Oops, F1, 2, and F2, 1. Okay, I'll let you do that as practice to verify those vectors. But you can just copy this verbatim, in your formula sheet or whatever. This is the way it is for oppositely pointing currents, okay? You get a repulsive force. So this is an attractive force, and this is a repulsive force. So it's kind of opposite to what we learned in electric fields and charges, right? Or electric forces due to electric fields and charges, right? Opposite charges produced an attractive force, and same sign charges produced a repulsive force. It's opposite here. So just remember that's opposite for current. So current carrying wires pointing in the same direction, right? Same is actually producing attractive force here, and opposite is producing repulsive force. All right, and there's two right-hand rules going on, right? The first right-hand rule is find B field right-hand rule. And technically we use the curl right-hand rule for this, okay? The second right-hand rule is find the force. And that one, you can use the curl method, or you can use the corner right-hand rule, which is where you have three fingers, right? Your thumb and your middle finger and right, something like that. Something like that. I'm going to learn. One day I'll be better at drawing hands the more I teach this class. Right? So the curl or the corner works for the finding the force, but for the finding the magnetic field, you're pretty much always going to use the curl one. Okay, so that's the brief summary. So that gives us direction of the force. So what about the magnitude? We can kind of derive the magnitude. So remember that the force, let's just do the force of 1 on 2. Well, that's going to be current of 2 times the length times the B field experienced by wire 2. Well, the B field that is experienced by wire 2 is the B field created by wire 1. So I'll just put that subscript 1, okay? ILB, and it's all 90 degrees, so the sine of 90 is 1. What is B1? What is B1 here? Well, B1 is mu naught I1 over 2 pi r, right? In this case, if we look at this picture, our r is d. So let's just go ahead and write d. So we're going to plug that into the force equation. Let's rearrange things to make it pretty. So let's put mu naught in the front. Let's put I1, I2, L over 2 pi d, where L is the length of the wires, okay? Let's say that they're equal length, so I'm just gonna leave it as L. There we go. That's the force that wire 1 exerts on wire 2, right? The force that wire 2 is feeling. Well, if we were to rederive it for the other guy, we would end up with the same thing, except we would have I2 LB2, which would just switch the position of I1 and I2. And we know that if you do that, nothing changes with the value, right? 2 times 1 is equal to 1 times 2. So you get the exact same answer. And so basically the two forces are equal in magnitude, in the same way that it was for Coulomb force, right? Remember in the exam, a lot of people missed that one, right? Those forces are equal because when you're finding the force K, Q1, Q2 over R squared, you're just changing the position of Q1 and Q2, which is just a multiplication, which equals Q2 times Q1, right? So in this case, the magnitudes are equal as well. And then the directions you get by doing, right-hand rule 20 times. Just kidding, just 2 times. So here, what we're going to be doing when we're working with wires is we're going to always be looking at the force per unit length. So we're going to always be looking at the case where the wires are infinitely long, okay? And so we're going to divide out by the length. All right, we're going to divide the length out, and this is going to be the magnitude. So this is going to be force per unit length, newtons over meters, okay? And we're always going to be dealing with that. So it's a very easy way to apply this equation here. And so there's an example in the lecture slides, example 19. Let's just look at it real quick. I'll let you guys do it. It's very straightforward example, okay? 19.6. So do this example. I'll post my notes on here on my, the full notes that I have written on the slides for you guys, since I'm kind of posting a shortened version of this lecture. I just want to get you to the information that you need, straightforward, okay? So take a look at this, and then that's pretty much wrapping up. Oh yeah, let's look at this got the concept real quick together. All right, so do that example. Let's look at this got the concept. It's kind of interesting. So there's the answer, but let's talk about it. So let's say that we have our coil, right, our helix. We're wrapping our wire in this helix, and it's a flexible wire, so it can move around. If we send a current in this way, what happens to the wire? If we send a current in this way, what happens to the wire? The idea here is we need to take a look at the direction of the current at these parallel locations, right? Let's look at the direction of the current at the side of the coil that's closest to us. They're all pointing to the left. And so, well, we're going to have parallel wires here, right? With the currents pointing in the same direction. And remember that same current is actually an attractive force. Okay? If we look at it here, the current is going into the page right here. And so again, you have parallel currents, okay? So all these parallel currents are going to generate an attractive force between the wires, and the coils will be pulled together. All right? So it's a pretty interesting problem. And that wraps up this chapter here. So in this last lecture, we just talked about magnetic fields created by currents. What direction are they? And then we applied the two fundamental concepts of this chapter, that currents feel forces and that currents create magnetic fields. We combine them together to look at the forces between two wires, okay? And that wraps up this section. I will, be available for questions if you need help with any of the homework. I posted hints, so keep in touch, okay? Have a good one.